Hi, chemistry students. Today we're going to look at waves and look at the relationship between wavelength, frequency, and energy. So first we want to look at the electromagnetic spectrum, which is the entire range of wavelengths of electromagnetic radiation. Now, electromagnetic radiation has both properties of waves and particles, and we're going to look at waves, wavelength, frequency, and energy today. Looking at the electromagnetic spectrum, you'll notice that there's only a small little fragment in there that's visible light that we can actually see. Everything that is longer than visible light we can't see, such as you can see here radio waves, microwaves, and infrared. Looking at things that are shorter in wavelength than visible light we also can't see, such as ultraviolet rays, X-rays, and gamma rays. So there's only a small fragment of electromagnetic radiation that we can actually see in that visible spectrum there. Anything longer or anything shorter, our eyes actually can't see it. But there are other things that can see those types of radiation, bats. We also have various insects, and other animals can see different wavelengths of light. So looking at electromagnetic radiation, the first thing we want to look at is the wavelength. And it's indicated here by the little symbol lambda. And so wavelength is the distance between two peaks, also can be called crest, or two troughs. So you can see here labeled on our wave, here is a trough, the lowest point of the wave, and here's another trough. And so it's the distance between those two. That same distance can be seen if we go from here, crest to crest, that also would be a wavelength. So you can look at the top two peaks or crest, or you can look at the bottom troughs between two waves, and that's going to be your wavelength. The next thing we want to look at is frequency, and this one's a little bit difficult to grasp for a second, but you're looking at the number of waves that pass a stationary point in 1 second. So if we looked at this being our stationary point, it would be the number of waves that pass. So we would be looking for every wave that went through. So when this one went over here, how long that one, we would be looking at that wave going through, and then we would see this wave going through. And so as we continue to keep seeing waves going through, we would need to have a certain time limit. So if we were counting them every second, how many waves went through in that particular second? If we were able to get 2 waves to go through in 1 second, that would be 2 waves for every 1 second, so 2 over 1, and that would give us 1 hertz. So our frequency would be 2 and then hertz, or Hz. We also can write this as 1 over seconds, or s to the negative 1 for our units. So you can write it as 2 hertz, like you see here. Hertz can be abbreviated as far as unit-wise as Hz. We also can see that as 1 over s, 1 over seconds, or the inverse seconds, or s to the negative 1 for our units on frequency. But again, it's the number of waves that pass that stationary point in a second. Amplitude is going to be half the vertical distance between peak and trough. And so what I like to look at here is, if we're given the x-axis, looking at the distance from the x-axis to a peak, I also could go here at the x-axis here and look downward to the trough, and that could also be my amplitude. But we're looking basically at the height of the wave, and that height of the wave also looks at the intensity, so how bright that is. The taller the amplitude, the brighter that particular radiation is going to seem to us. So what is the relationship between this wavelength, frequency, and then also energy? Well, the shorter wavelength, the higher the frequency and the higher the energy of the electromagnetic radiation. So if we're looking at the list of our electromagnetic spectrum, you'll notice that on the left-hand side of that electromagnetic spectrum, radio waves had the longest wavelength, which means that they are going to have the lowest frequencies. So you don't have as many of the waves passing a given point per second. It takes them longer because they are longer in wavelength. And then you also have them having the lowest energy. So again, if we look at infrared, which is heat, us standing in front of a heater or some kind of heating source, we're getting IR radiation. And the reason we can stand there for so long versus being out in the sun where we are getting exposed to UV is because IR compared to UV has longer wavelengths, and so that IR radiation has lower energy, and it's not able to, it's longer and can't go into our skin and start ionizing or messing up our DNA. If we look over here at gamma radiation giving off by nuclear reactions, that has the shortest wavelength, so it's going to have the highest energy. It's also going to have the highest frequency, so you are getting a lot of radiation per second. You're getting a lot of those waves hitting you if you are the given point per second, and those wavelengths are extremely short, so they can go through your skin and they can start damaging your DNA. Same as x-rays, which is why you are limited to the number of x-rays that you can have per year and types that you can have per year, which is one reason why when you go to the dentist you don't get your teeth x-rayed every single time that you go to the dentist. Normally it's only once a year as necessary, and they also limit where that x-ray is going to be taken, so they have one little spot that they're actually shooting with x-rays versus x-raying your entire head or your entire mouth at the same time. So they basically are going to shoot in certain areas and take only a few pictures of your teeth to limit the exposure to the x-rays. So looking at these, which wave has the largest wavelength? Now, if you look at the picture, you'll notice that the largest distance is actually happening from this trough to this trough. So this one actually has the longest wavelength when we're looking at the waves themselves. E would actually have the shortest wavelength when we look at the distance from trough to trough. That has the shortest wavelength. We also, looking at our electromagnetic spectrum, you can see that, if you remember, Roy, G, Biv, so this would be red, orange, yellow, green, blue, indigo, and violet. You'll notice that red has the longest wavelength, whereas violet has the shortest. So here, looking at the pictures and remembering our visible spectrum, Roy being red on the left has the longest wavelength. So A is our answer here. So which wave has the highest frequency? Remember that if you have a long wavelength, that's going to equal a low frequency. Why? Because it's taking longer for waves to go past that point. It's going to take them a longer amount of time to go through that given point, so you get less wavelengths per second going past that point. So which one has the highest frequency? Well, you are looking for the one that has the shortest wavelength. So short wavelengths don't take as long to go past a given point per second. So they will have higher frequencies. So here, our shortest wavelength is E. The distance between trough to trough is extremely short, and it has the highest frequency. So now let's look at energy then. The wavelengths that have the highest energy are the ones that are going to have the highest frequencies, the ones that you're getting the most waves to pass a point per second. So if it has a short wavelength, such as E here, then that means you're getting more waves to pass a given point per second, which means that's going to have a higher energy. So, short wavelength, that means more waves passing a given point, so high frequency. And since we're getting more waves to pass a given point, so high frequency is also going to give us high energy. So things such as UV light, X-rays, and gamma rays are going to have our highest energies. And here we can see that violet on our Roy G. Biv, violet here is going to have our highest energy. It has our shortest wavelength. So which color of light has the longest wavelength? So if we look from longest to shortest, we've got Roy G. Biv. Our longest wavelengths happen on the left-hand side, so this would be red, would have our longest wavelength. So looking at our answer choices now, we have orange, green, blue, and violet, red being our longest, violet is our shortest, that means that orange here, our O, is going to have the longest wavelength. So which type of electromagnetic radiation has the lowest frequency? Well, if we look at our electromagnetic spectrum, at the top of our note sheet, you'll notice that our longest wavelengths start here on the left, and they go over to the shortest. We also know that long wavelengths have low frequencies, and our shortest ones have high frequencies. So looking at our electromagnetic spectrum from our notes, we notice that radio waves are going to be the longest, and if they are the longest, then they have the lowest frequency, so A. Radio waves will have the lowest frequency out of all of them. It's going to take them longer to pass a given point per second. And example 3. Which type of electromagnetic radiation has the highest energy? Going back again, looking at the top at your electromagnetic spectrum, we have long wavelengths, and our short wavelengths are going to be on the right-hand side. Long wavelengths give us low frequencies, not as many of them passing. And short wavelengths, we get high frequencies. So the lower the frequency, the lower the energy. Less waves are passing that given point per second. We're going to get low energy from those. High frequencies, we're going to get high energy. Those are going to be your high energy radiation. Those are going to be the ones that will damage your skin, damage your DNA, can cause cancer, such as ultraviolet light. If we stay in the sun for too long, it damages our skin and can cause us skin cancer over a period of time. So the shorter the wavelengths, the more damaging they are to us and to our DNA. They can get into those places because they are, again, so short. And you're getting large doses, you're getting a lot of those waves in a short amount of time as well. Also, they have very high energies. So if we look at this question, it's asking us for the ones that have the highest energies. The one that's on the farthest to the right with the shortest wavelength and the highest frequency, and of course the highest energy, is our gamma radiation, found and given off in nuclear decay reactions. And that's all I have about wavelength, frequencies, and energy. There is a YouTube video that you can also watch. This will be attached to your website from your teacher for you to watch on the electromagnetic spectrum. It's a very short video. Please click on that and watch that also tonight.